Hello, I'm David Cavuto, Director of Product Management for Search at Cribl. Today, I'm going to be showing you a new feature of Search called Notebooks. Notebooks have been in preview for several releases, but it was finally released at CriblCon in October of 2025. So this demonstration applies to the 4.15 release of the Cribl Cloud platform. In particular, to show it off, I'll be using it in combination with the Lakehouse feature of Cribl Lake product. Today, we're going to create a new notebook and use it to describe the process we'll follow. Note that each notebook is organized into cells, and each cell can either be a note or a search. The first cell you get at the beginning of a new notebook is always a note cell. Note cells are formatted using markdown. You can see a few examples of this formatting when you click on any new note, but they will get overwritten when you start typing. Let's call our top level note Investigation, formatted as a header 1 using a single pound sign, a hash mark. Next, we're going to make a second level header powered by Cribl Lake and Lakehouse. I'll put my name on it as well. Now that I've created our header, I'll paste in the process we're going to follow for this investigation using Lake and Lakehouse. Number 1, we're going to look at our federated search dataset, something that's in S3. 2, we're going to isolate some events of interest. 3, we'll go into search and run an export command to export those events from S3 to our Lake dataset with an attached Lakehouse. And 4, we'll do some fast ad hoc investigation. All of this will be tracked using our notebook to follow all the steps in this process. Clicking elsewhere in the notebook will save your note and render the markdown as formatted text. Incidentally, if you've never used Markdown, I recommend markdownguide.org/cheat sheet to give you some basic overview of some formatting elements that you can use. Before we start using our notebook, let's make sure we have a temporary place to store the data that we're going to explore. To do that, let's create a Lake dataset and make sure it's connected to a Lakehouse. If you've never created a Lakehouse before, please see Cribl documentation or other videos on how to use the Lakehouse feature of Lake. Let's go to Products Lake and then look at Lake datasets. From here, we can add a Lake dataset. We can call this dataset Lakehouse_investigations. Let's choose an existing Lakehouse. On this Cribl Cloud organization, one Lakehouse already exists called Hot Sauce, so I'll choose that one. Finally, I'm going to tell it that I would like to partition by a field called tag, which we'll talk about later, and index the Lakehouse also by that same field called tag. Note that we can keep this data for as long or short as we'd like, since it's just a temporary copy of what we've already got in our S3 object store. So for this example, we'll set it to 60 days. We'll hit save, and we can see the created Lakehouse at the bottom of the list called Lakehouse_investigations. Now just to check, we can click on Lakehouses and see that the Lakehouse is called Hot Sauce, and hovering over the datasets field, we'll see that Lakehouse_investigations is one of the datasets that's associated with it. Also, to verify that the Lakehouse is empty, nothing's up my sleeve, as the magicians might say, let's go into search and quickly verify that. Running a quick search, we can see that in fact there's no data in the dataset. However, we can tell that the Lakehouse is active by this icon here in the search status bar. Now that our environment is set the way we want, let's go back into our notebook. Step 1. Let's identify some data of interest from the relatively slow object storage. In this example, I'm going to use our old standard Cribl Search sample. But you should target any federated data that you'd like to investigate. We'll start by taking a quick volume summary of that dataset so we can understand what we're working with. To do a time-based summary, we use the time stats operator and set span equals 1 day to count the number of events by data source. We could pick a longer time period here for a summary, so let's choose 14 days and start the search running. There we go. That search took about 40 seconds. If we want to, we can stack that data to see what it looks like. Quickly highlighting some more of the notebook features, recall that I mentioned the notebook is organized into cells, note cells, and search cells. Each cell can be moved up and down to rearrange them. You also have the ability to lock or unlock the notebook, which will prevent accidentally modifying or changing the notebook in any way. Step 2, we'll isolate some events of interest. Now that we've surveyed this overall data set in object storage, let's isolate one smaller set to move to our Lakehouse so we can investigate it more fully and quickly. If we choose Access Combined Data on November 27th, incidentally Thanksgiving Day in the US, we have about 1.7 million events right here. The easiest way to move this data to Lake and Lakehouse is to use the export operator in search. Export is explicitly designed to easily move data into Lake. If a Lakehouse is associated with that Lake dataset, the export operator also automatically inserts the same data at the same time into the associated Lakehouse. Since we're going to take another step using the search we've already created, let's just clone this cell. This is an operation we'll be using a lot moving forward, so let's get used to it now. We'll add data source equals access common here in the search bar, and then open the time picker and choose an absolute earliest timestamp here, November 27th at midnight. We'll also set the latest timestamp 24 hours later to the following day at midnight, so we've got a full day covered. Note again, this is just an example. For your dataset, choose the specific events of interest, which may involve a more complex search expression. If you're investigating a security event or an IOC, you may want to filter on source or destination host or IP address in a given time period. Now once you've made that filter, let's do a quick count to make sure we've got it right. We're expecting it to be about 1.7 million events, as we saw earlier. Let's run that search and expect that it'll come back a little faster since we've isolated a smaller time period. Good. 1.7 million events is exactly what we got. Now that we've got a rough idea of how much data we're going to be exporting to our Lakehouse, we can do that pretty safely. Step 3, exporting our events of interest to Lake. Now we want to use the export command to get the raw data out of that affordable but slow object storage and into the fast and flexible Cribl Lakehouse. As a reminder, Lakehouse is a pay-one price feature of Lake where all searches are included. That means you can search as much as you want into a dataset resident on Lakehouse, and you pay only the Lakehouse price. Looking back at that export search, let's make sure we tag our data. Recall that we instructed the Lake and Lakehouse to make special partitioning and indexing decisions based on a field called tag. The way we do this is by simply adding a new field using the extend operator. Tag equals raw underscore data underscore 2025-11-27. That's a human readable label that we can use to reference a subset of the data in that data set, but will also be treated as an index for extremely fast retrieval. Finally, let's finish our export operator to export the data to the Lakehouse underscore investigations data set. We'll execute that search, which should take about 90 seconds. We'll skip past so you don't have to wait. Okay, it's been about a minute and a half. We see that the export is complete and we've got quite a few events. Each of these export events is essentially a log showing its progress. The last event, shown at the top, is the export complete event. Finally, we're in a position to start our investigation in earnest. All further searches will be performed on the Lakehouse underscore investigations dataset rather than the original federated S3 dataset. That will make each step of our analysis significantly faster, allowing for more flexibility and what-if analysis. Step 4. Let's perform some fast ad hoc investigation using Lakehouse in our notebook. I'll create a new search from scratch now, since we're not going to reuse any of this earlier search elements since we've got data of interest in its own data set. I'll start by searching into our new data set, Lakehouse underscore investigations, and then add that tag we referenced earlier to create an index. We should be able to very quickly get those results. And now you should see that this is a significant difference doing an investigation in Lakehouse versus doing it in your original federated object store. 1.7 million events, half a second, versus what we saw earlier, 5 seconds, 40 seconds, or 90 seconds it took to dig through all of that data. Now that we've got our basic search template, let's clone that search again. We'll take a quick sample of that data set so we can see its basic structure. Great, it's exactly what we sent from the S3 bucket, but now it's lightning fast. As an analyst, what could we do with that data? Well, why don't we try pivoting and aggregating by the client IP field? We'll add summarize count by client IP to the search. Cool. We have a pretty even distribution of all the client IPs, 99 different ones. Unsurprising since this is generated data. Notice I keep going back and referring to my original data. That's showing the power of the notebook. Our analysis path is retained for simple and fast reference. Next, we could, for example, look at the request field and pull out the first element of the path inside the request field. That's often useful when looking at URLs to see if there are any hotspots in case of access or potential areas of attack. Since the whole request is stored in a single field, how might we do that? Well, we can use the split function here. I can use the extend operator to create a new field called firstPath, for example, and set it to the value of the function split with some parameters. Hovering over that function in the search UX, we show a pop-up with help on how to use split. We want to pick up the source field and then specify a delimiter character. In our case, we're splitting by the request field, and we want to use the / character as a delimiter. Although the split function can return an array of all the split fields, we actually only want one particular field, so we can specify index field 1, which is everything between the first and the second delimiter, in this case /. Let's run the search to see if that worked. If we turn the detail panel off so we can look at the full events in place, here we can see request field head /open-source/enterprise. And we know that our desired field is stored in the field firstPath with the expected value open-source. So now that we know that that step worked, we can clone that search. I said we'd be doing that a lot. The next analysis we can do is to produce a combination of summarize count by client IP and firstPath based on that split function we used earlier. Look at how fast that search returns data over those 1.7 million events. Now, since this is randomly generated data, we can see that we pretty much have a similar breakdown of client IP firstPath combinations, about 17,000 for each one. So again, no hotspots. Your data will likely look very different. For one final dimension of analysis, let's take a quick look at HTTP status codes. We'll change the search to summarize by a count of each status code. Maybe let's visualize those as a donut chart so we can see different distributions. Kind of looks like 301 stick out as the highest value. But if we sort them by this, we'll actually see that 304 is actually the highest. So now from here, we'll clone that search and tell it specifically to look at 304s, and then look at which one of the client IPs are generating those 304s. And then we can also look back at that firstPath field that we generated earlier and add that back in as well. Finally, if we could take that, put it in a column chart to see if there are any commonalities between firstPath and client IPs. Nothing specifically pops out, but no surprises given the source of this data. I do want to summarize our experience here so far. We spent some time finding data of interest in our slower S3 object storage. Once we identified that data, we moved it to Lakehouse using the export command. After we moved that subset of data into Lakehouse, every single search has taken less than a second to execute in Lakehouse. 0.69 seconds, 0.82 seconds, 0.53 seconds, 0.74 seconds, 0.79 seconds, and 0.82 seconds, all less than a second. This notebook now has a record of all investigation we performed and can be kept for an arbitrary length of time. So what we're showing here is that by taking the upfront time to move your data to a Lake dataset that has a Lakehouse associated with it, you can perform very fast ad hoc investigation of this Lake dataset. But you can use notebooks to track all of the steps in your investigation process. Now if I return to my Notebooks tab, I can look all the notebooks that I've created, then I can go back and jump into this specific notebook at any time and review my process. I can even go back and add annotations. Like, for example, I can note this step where we move the data explicitly. I'll add a note saying data move step. Takes a little longer time, but results in shorter work, which is the point. I'm doing all this with the markdown characters that I noted before. So the upshot of this feature is that the notebook functionality tracks my entire process. Any follow-on investigators can see my process, understand the conclusions I've drawn. No need for separate annotation documents or spreadsheets to track. In fact, each notebook is fully equipped with RBAC authorization, so you can use the Share button to specify which members of your team may have access to it. Notebooks have similar RBAC commands as do datasets and dataset providers. One last notebook feature to highlight, that is the AI summary button. This feature generates a natural language summary of all the steps you took, examining both your notes and the Cousteau syntax in your searches, and summarizes what you did so the casual reader can follow your logic even if they don't understand KQL. In our case, the AI summary did a great job. It followed that we spent time isolating events of interest in the object store, then exporting those events into our Lakehouse. It also noted the specific types of investigations we performed once we had the data in our high-speed analysis system. It even commented, as we saw, that the client IP addresses were evenly distributed. It suggests some next steps we could take. This is an excellent executive summary of all the analytic steps that we just performed. That's all I've got today. Thanks for following along with this summary of Cribl Notebooks, powered by high-speed Lakehouse feature of Cribl Lake. My name is David Cavuto, and as always, I wish you happy searching.